Good afternoon, everyone. Today we want to show that such an expression as this, differentiating this expression with respect to this, will be equal to that. We solved a couple of problems like this the last time when we talked about our exploiting the properties of the Christoffel symbol. So before I begin, I'd like to make an attribution to this problem majorly to Joe Weber's book. So we'll continue as we did the last time. So very quickly, in order to differentiate this, first you can see that this mu and nu doesn't have mu in any way like we had in last time. Last time we already solved such a problem for which g mu was contracted with the lower indices of the Christoffel symbol. And then we solved the one for which one of the indices on top, one of the index of the Christoffel symbol, the one on top, was contracted with the one below. And a combination of those two results helped us to solve the one that had to do with one for which two indices contracted with this, and then one on top and one down. We didn't even have to do so much for that touch problem the last time we met. But this is a little bit different and quite a little bit more involved than the others, because the mu nu, we have mu nu here, we have dummy indices alpha, beta in this way. So they are connected in such a way as to make it difficult to be able to make anything that simple, or such that we can apply the previous results that we obtained in our calculations. At this point in time then, we try to find a way regardless of how to solve it. And a very important formula in this regard would be this. Of course, we know that the covariant derivative of the metric tensor is always 0. But writing out the formula in full will give us this. First of all, we'll have to simply differentiate the tensor with respect to x beta in this case. Plus, we'll be contracting one of the upper indices on the metric tensor, this time around mu. And I'm using mu to do that. I'm differentiating with respect to beta, it comes over, and that which I'm contracting moves over to the Christoffel symbol. And then plus, the same thing, I'm contracting alpha this time around. I leave mu alone, so the alpha just joins the Christoffel symbol. The nu replaces is contracted. Of course, that's what we intend to do. We are differentiating with respect to beta again, and so it comes along. Now, what is our intention in this expression? Well, you can see from this expression at this point in time that something like this, which we are going to find very useful very soon, we can make this particular term the subject of the formula. Given that all this is equal to 0, we can see right away that g mu nu gamma alpha beta nu is equal to minus of g mu alpha comma beta minus gamma beta nu mu g alpha nu. That's what we'll get. Okay, let me write that in a way again that will make this a little bit more apparent. The left-hand side on this equation simply could be written as something like this: g mu nu, and then I can write the gamma alpha nu beta here at this point. Of course, then combined here, I simply have the other Christoffel symbol, mu alpha, and then the square root of minus g. And this is what I get. This is all differentiating with respect to g rho sigma comma gamma. So everything we have here is the same. I simply just join this to the Christoffel symbol so that I can have it in this form. Why is this important to me? Because I can then write this as, say, the g mu nu gamma alpha nu beta, here g rho sigma gamma. Then I have here following me beta mu alpha square root of minus g, and then plus I have just the first factor which I differentiated previously. So this is the basic Leibniz rule: gamma beta mu alpha square root of minus g, here the g rho sigma comma gamma. Okay, well, I think we've gotten ahead of ourselves in this. Sorry, what I would like to do actually, because that is one way to go about this, but I think very quickly and immediately, I would like instead to make this substitution. D, then here I'm going to have minus G mu alpha comma beta minus gamma mu beta nu G alpha nu. That is from here. Given that this expression, I have called it out like this. Just from here, I showed that connecting this and this gives me that. But I've shown from an expression such as this. Please know that I actually obtained this, not I have to try to find out each time. I have to try to find out which will be most suitable or in whatever way this formula will be of help. So I use something like this. So instead of having this following me about, I simply put that in place of it. But then, of course, I still will have to write this again. Mu alpha square root of minus G. That is what I would rather do. G rho sigma comma beta gamma. So what we did initially was quite okay, but this I believe will be better for us. Now I'm going to combine this. Of course, obviously I have two terms here invariably. There is. So I'm going to have here with me. So let me pull out the minus sign. It's going to be some the G mu alpha comma beta, and I'm going to be multiplying this with gamma beta mu alpha square root of minus G. That is what I will have. And then I'm going to have here the G rho sigma comma gamma. That would be the first term. Then here I have with me minus. Of course, then that will be again the G. So let me put this first. Alpha nu, gamma beta nu, mu here. Then I have gamma beta mu alpha square root of minus G. And this is what I have for the second term. G rho sigma comma gamma. Yeah. Okay, let me just try again to perform some index changes. For this, I would like to interchange beta and mu. For this, I would like to interchange beta and mu. My intention is, if you look at this term here, I have a metric tensor with a Christoffel symbol, one more here, and then multiply by square root of minus G. I have a metric tensor, two Christoffel symbol and square root of minus G. So this second term is already somehow beginning to look like what we have on the left-hand side. So my intention is to see, since they're all fraught with dummy indices, to see how I can make any changes. Maybe we might be lucky to be able to change this second term into this. And if that's the case, then we can move this to the left-hand side. So that's the essence of this transformation. So here at this point, I'm going to have minus D here, G. I said I'm interchanging beta and mu. So what I'm going to have here is beta, alpha, comma mu. And then here I'm going to have gamma mu. And then here I have beta, alpha. And this will be the square root of minus G. And now I have that the G rho sigma comma gamma. Next, I will have minus D here, G mu nu gamma. Okay, sorry, because I said I was interchanging beta and mu. So this should be a beta, and this also should be a beta, and down here then becomes mu, and this is a nu, and then gamma, I have this should be a mu, and then I have that this should be a beta, and I have a mu, and then I have the square root of minus G, and that is that. Now I'm going to have the G comma gamma. So looking again at what we've got here, I have an alpha as one of these indices here. I have an alpha, but what I've got here is there's a mu. Well, the original expression does have a beta. So on this note, I will try again now to perform such a transformation as changing that and that on that second term. Of course, I'm still leaving the first term all alone. For now, it doesn't even look in any way like the first term, so there's no point bothering ourselves with any more index transformations on this first term. Comma gamma. Now this is minus. I said I'm interchanging alpha and mu. So this is unchanged, not affected by that. Beta. Mu here becomes alpha, and this is nu. And gamma here, mu here becomes alpha. The beta is here, and that is nu. Of course, And then this is, sorry, so this is not like an interchange between alpha and mu, because I don't have any alpha on that term. But it's to tell you that it's a possibility, because mu is a dummy index, so I can just by will change, actually, so I can change mu to alpha. So this is a possible transformation. I can perform that transformation because mu there is a dummy index. Okay, so looking at this again, what else will I want to do to make this almost the same? I've changed mu out to alpha, and then I have mu here. We have got here with us nu. And also here, the mu here is alpha, so we've got two nu's here. So there is something else I can do here. I can change beta to mu. Yeah, I can change beta to mu. So first of all, I can change beta to mu, but then if I do that, I'll have a mu here, and I'll have a mu here. And this mu here that I already had to become alpha. So sorry, this is quite unnecessary for me to have made that transformation. I'll leave it all alone. So this remain mu without making that transformation. This remain mu. So what I would like to do now is actually make an interchange between mu and beta. Yes, I want to make an interchange between mu and beta. I think quite later. So without writing the first time, let me see if this is leading anywhere anyways. So this is going to give me this gamma, and so this is supposed to be a mu, and the mu there becomes a beta nu, and this is another gamma. This mu here becomes a beta, the beta here becomes a mu nu, square root of minus g, and then all over this is the g rho sigma comma gamma. Now please just take a look. The Christopher symbol with a mu on top has beta nu down. So here we have okay, so maybe eventually I will have to change one of these to alpha. It's no problem, even if we keep moving around and round about this. So this is beta mu down here, so I have nu beta. So my intention here would be to change this to sort of alpha, and it's occurred twice. If I did that, I'll have the one with beta with down mu alpha. So you can see this will become mu, sorry, is that mu alpha? This is, yeah, nu beta and mu alpha. So if I change the mu here, to alpha, then I'm going to have just as I have here, and I'll change the nu, I'll interchange nu. So first of all, I'm going to make an interchange between mu and nu. If I made that interchange between mu and nu, so without rewriting it in the next step and occupying space, I'll simply make the interchange between mu and nu. Of course, the metric tensor remains the same. So this becomes a nu, this becomes a mu. Mu and nu, of course, nothing changes here because, like you know, this will be, it will become symmetric, so nothing changes. So what then do I do next? I simply change the nu, so in my next interchange, I'll change the nu to alpha. I think we're here then. So this will be minus the g beta alpha comma mu, gamma mu beta alpha square root of minus g, and this will be the g rho sigma comma gamma. And with that being said, you can see that finally when I make this change, or which maybe I should do right away to avoid having to write the whole expression all over again. If I do that, what I'll get is alpha and alpha, and I believe at this point in time I have alpha mu here with beta on top, right? And the other one with alpha on top has beta mu, or beta nu. I performed an interchange between mu and nu, right? I think that's what I did between mu and nu. I must have had a mistake somewhere here, so that. Also, sorry for the mix-up, please. The issue was already from here. I actually mistakenly copied an alpha here as nu. I've changed that already, as you can see. So everything actually should have been from here. As you can see, what we had originally was this. So what I'll simply do, like I've said before, it was an interchange between mu and beta. I have two betas here and two mu. So the only changes I'm expecting is here, these two changing to beta and these two changing to mu. The nu and alpha here remain unchanged. And as you can see, I have them now beta, beta, and what is here is now mu, mu, nu and alpha. So my next step, I decide to make an interchange between alpha and mu. And with the idea, of course, of trying to make this G mu nu, since I have an alpha here. So if I do that, the two alphas here become mu's, and the two mu's here become alpha. And that's what I've got on the next term. Now, this time around, I perform an interchange between mu and nu. The metric tensor here remains the same. And if I perform that, the mu here comes here and the nu comes over here. And this is what I have. And this time, as you can see, is just the same as what we had on the left-hand side. So if I were to continue with this problem, what I've got is simply this one going over to the left-hand side, which was what we started with, adding it all together, dividing both sides by 2. So what I can say simply is that actually the G mu nu, gamma beta, alpha mu, and then gamma here, alpha beta nu, square root of minus G, and I'm differentiating this respect to G rho sigma, comma gamma. This then should be equal to, because of this minus, I'm going to pull out the square root of minus G, is obviously independent of these objects. Differentiating with respect to this gives us 0. And I'm dividing by 2 from the fact that when I add this to the other one on the left hand side, I get 2 times of it. And so I have here with me the G beta alpha, comma mu, gamma of mu beta alpha. And this gives you here, so I have to be careful with indices again to avoid all these trouble. So this is G sigma, comma gamma. This is what we've got. Looks like we've made a headway. Well, we're just getting started, but at least it looks quite simpler than what we had initially. And if you look at this, I'm sure probably someone else may find another way around this. But this, for me, is something I think is one way by which this could be done. So looking at this now, we're going to make another identification here with what we had originally, which was this. This was given to us by this expression. So as a matter of fact, I can just start over again from this place, since we're done with this, everything written on this part. So in order to make things very easy for me, I'm not having to write the left-hand side. Please, I'm going to call this some capital letter N. So I will have to write it every now and then again. So capital letter N is equal to here minus the square root of minus G all over 2. And then I have that to differentiate D of G to make sure that beta alpha, comma mu, and what I've got over there is gamma mu beta alpha. And now I'm differentiating this with respect to G rho sigma, comma gamma. Okay. Now at this point, we've got to, like I said, substitute just directly. Of course, you can see I planned this ahead to make sure that my formula looked exactly like this. So it doesn't matter. Even if you had this written some other way, in terms of other indices that are not similar to this, you can just, of course, from that, be able to write it in this form. Now at this point, I will simply say that this is the same. So I'm going to say minus the square root of minus G all over 2. D, the G here, rho sigma, comma gamma. And what I'm going to have in the bracket will be some G, of course, because I've got here with me. I think what I'm going to do is actually make a separation here to make this all simple for me. So I can write this as minus the square root of G all over 2, so have 2 terms, sort of the G beta alpha, comma mu, the G here, rho sigma, comma gamma, then times this beta alpha plus G, I don't need to put that in parentheses, plus G beta alpha, comma mu, then that alpha the G, comma gamma. Yeah. I think that's a better way to go. So I can deal with this one at a time. Well, I don't think at this point. Well, okay, so fine. The next thing I'm going to do is just to write this again. So this is minus, and I have here with me alpha comma mu, and then here the g rho sigma comma gamma times this beta alpha plus g beta alpha comma mu. Now I'm going to say the g rho sigma comma gamma, and then in a curly bracket I'm going to have half 1 over 2 of some g mu nu in the bracket g mu alpha comma beta plus g, I'm guessing mu beta comma alpha, but minus g, this should be beta alpha, yeah, alpha beta comma nu. That in the curly brackets, and then finally there. Okay. Now at this point, you can see something. We actually dealt with something like this last time when we performed this calculation. So this might be quite simple. But the second time we can see something here. We have a metric tensor. First of all, yes, that's one thing that we've got. Of course, differentiating the metric tensor with respect to this would be 0 always. So maybe we wouldn't have to bother ourselves with that. But then, just moving on, let me deal with that first. Here is this. Excuse me. The first term here looks like this. This is beta alpha rho sigma. I remember last time when we dealt with this, we talked about the symmetries between these two. Because I could have written this as g alpha beta comma mu, and this also g sigma rho comma gamma. And so we symmetrize this expression when we perform the calculation. I wouldn't want to go through the whole process of explaining how we did that. But if you looked at that particular video, or you watched that lecture, you will agree with me that that first term will simply be equal to minus the square root of minus g all over 2. So the first term will simply be 1 all over 2. This will be Dirac delta beta rho. And then the next that follows it will be Dirac delta alpha. And what will be down there will be sigma plus. Yes, exactly. That will be sigma plus. I simply make an interchange. The next thing there will be Dirac delta. Instead of alpha beta, so I'm going to have alpha rho, and then Dirac delta here, beta sigma. Multiplying them all will be Dirac delta of gamma and mu. So mu on top and gamma down. So one other thing I've got to know, I have to say, is that in order to make this easy for me to avoid confusion, which might arise, is that I've decided to make, even though a conical delta, it doesn't matter which you keep on top and which below, but I've just decided to make sure that the alpha and betas are all on top. The mu also is on top. If you look at this, the alpha and betas are all on top. And by our symmetrization process or procedure, this is what the first factor will give us actually, because this is multiplied by some gamma, mu, beta, alpha. That is that. Now, the second term is what might look a little, how am I going to put it? Yeah, a little subtle, because first of all, okay, well, let me write it just like I said I could. Yes, I could, because I could say this is the same thing as 1 plus g mu alpha comma beta. Yeah, no. See, this kind of mistake that runs one into very serious trouble. Beta alpha comma mu, I believe that's what it is. And that's what I've got here. That's what it's been right from the beginning. I just want to make sure that I've not had any reason whatsoever for any trouble. We've made some identification, and it was in our making this a subject of the formula that we had. Was that going to be beta mu? So now we're talking. Please, I remember in our process of solving this problem, what we had originally, okay, so we made some changes. Yeah, we interchanged initially beta and mu, and that was because of the fact that I had this. So even that which multiplied it from this side, I connected this and this, okay, became a mu. Okay, well, I think we're all good. just to make sure that this doesn't cause me any troubles when I start or when I begin. So the next thing that we're going to have is plus. I'm going to pull out this metric tensor. By the way, I can pull out the 2, the half here 2, and the G mu nu, so that all I'm left with is this, rho sigma comma gamma, and this will be multiplying, I don't need a curly bracket, I can simply say G nu alpha comma beta, that's what that should be, plus G nu beta comma alpha, but minus G alpha beta comma nu. Again, making sure exactly that's what it is. Now this is what we have. So if you look at this expression here, I've simply pulled out 1 over 2 times this out to meet with this, so that this will simply be left to act on this expression. Okay, now so this is what we have here to deal with. In this expression of factor, you can see that for the metric tensors here, I have them to be covariant metric, or you can say the inverse metric tensors. But this is just a metric tensor. The indices are not on the same side. And so I can't add with this directly on this. It's certainly not going to be 0, because we know that all these are also, these are derivatives of some metric. This is also derivative of some metric. So you can't with certainty say the derivative of one metric with respect to another is 0. And we can't tell exactly what it is really also, given the fact that they are not of the same covariance, whether contravariant or covariant. So I have 2 options. Either I make all the metric tensors here contravariant by raising the indices here. There will be a lot of metric tensors following us around. Or I can decide to lower these 2. And if I do, I wouldn't have to lower or raise anything here. All I have to do is, if I lower these 2, then I will have a metric tensor derivative that looks just like the ones here in the bracket. Then I can use that to operate on this expression. So, and then looking at this term here, I think the very wise thing to do is to keep evaluating this as we go. Minus the square root of minus g all over 2. And what I've got here is 1 all over 2. Here, I've got with me alpha and beta for the first term. I've got with me alpha and beta. So here, beta, alpha. So what I have there is for the first term, I'm going to go in with the gamma mu, and this, just to avoid any confusion for the first time. But the alpha and beta have got to change. And they will have to change. First of all, the beta will be a rho, and the alpha there will be a sigma, as you can see. That's what it should be. Plus, I'm going to have again gamma mu, and this again following me about. The beta this time around again will be a sigma, as you can see. And the alpha will be a rho. That is by evaluating those conical deltas. And then here I'm going to have, okay, I think the best thing for me to do is to write it out here. Plus g beta alpha comma mu all over 2 g mu nu. Now d, I'm going to have 2 metric tensors. Let me say rho delta and g sigma eta. And this will become d dg delta eta comma gamma. And now what I've got here is g nu alpha comma beta plus g nu beta comma alpha minus g alpha beta comma nu. And this is what we have. So this first metric tensor was used to lower this rho. And when it lowered, it became a delta. And then this second metric tensor was used to lower the sigma. And when the sigma was lowered, it became an eta, comma gamma. So I have 2 extra metric tensors. Moving on, again, minus the square root of minus g all over 2. What have I got here? Half. Again, it means if I'm expressing these metric tensors, conical deltas, I have here with me the mu becomes a gamma, rho sigma plus. Here again, I have a sigma rho, which by the way, wouldn't matter. Another gamma, and that is what I've got. Now, plus, I have here with me, okay, let me say g beta alpha comma mu all over 2. I have here g mu nu. So I can say g rho delta inverse, g sigma eta inverse, Okay, well, let's try to sandwich all that here. G delta eta wouldn't actually matter if it is eta delta or delta eta. Delta eta gamma, and then I have here with me G nu alpha comma beta plus G nu beta comma alpha minus G alpha beta comma nu, and that is what I've got. Okay, so now these of course obviously are the same. Adding the two of them, I get twice of that, but they have a half that is following them over there. So the first expression there is simply this, because this is symmetric of course in terms of the position of the sigma and the rho. Next, I have here with me plus some half G beta alpha comma mu, and then here I have G mu nu. Then I have here, the inverse of this becomes rho delta. The inverse of that becomes sigma eta. And then here I have with me the G. What I've got here is delta eta comma gamma. And here I have G nu alpha comma beta plus G nu beta comma alpha minus G alpha beta comma nu. Okay, now that is it. We're done pretty much with this first term. What will be troublesome is what we have to do here. Not very troublesome, but will be troublesome anyway. So, looking at this factor, I think it's preferably I just stick to this part of the board. So I'm going to clean this all the way except the last expression, and copy out that last term to work on it first of all, to see what I've got and what it might give us. If it is going to be of any help, well, yes. So I'm going to be working on the entire two terms. And for now, let me call this whole thing, just to keep me, since I've got something called n already, which is the entire thing that we're doing right now. Let me call it n sub 1. Let the whole factor be n sub 1. So that here, I'm going to have in bracket multiplying it. So what I'm doing right now is simply dealing with the second term. I'm ignoring everything else that we're doing so far. And by the way, remember that n was what we call our original expression, which was this left-hand side. And n is actually equal to everything here that we've gotten so far. So the entire thing here is what I'm looking at. So I think I would like to use a curly bracket. So the curly bracket here says, the G, the first one I've got here is nu alpha comma beta, and I'm differentiating this with respect to some G here, eta, delta, or whichever order, except that of course gamma is staying on its own, and plus here the G nu beta comma alpha, and this is going to be the G delta eta comma gamma. And then minus, of course, because that's what we've got there, the G alpha beta comma nu, and then I have here with me the G delta eta comma gamma, and that is what I have. So see why I said it's troublesome a little? Because then I'll have to perform the same symmetrization for each and every one of these terms. So in essence, this is equal to some n1, so I'm going to use some block bracket. This is supposed to give me 1 over 2. Now, like I said, delta of nu correspondingly, and this delta of alpha, eta, plus. Delta, this time around, I interchange. Alpha, delta, I bring nu over here, eta. Then that which is common to both of them, beta, gamma. And that's just the first term over there. Next, plus. 1 over 2 again. Delta, I have here with me nu, delta, and delta, beta, eta plus delta interchange, beta, delta, and delta here with me, nu, eta, and then I have here with me delta of alpha, gamma. That's what I've got. The delta, alpha, gamma is common to both. Then finally, I have a minus 1 over 2, another symmetrization. Delta of alpha, delta of beta, eta, plus delta, I put beta instead, delta, and delta of alpha, eta. Common to all of it is delta nu, gamma. And this is what I've got.